Welcome to Electrostatics and Charge Part 3, where we'll be looking at electric field lines with multiple charges, conductors and electric fields in static equilibrium, and a quick look at the Van de Graaff generator. Drawings using lines to represent electric fields around charged objects are very useful in visualizing field strength and direction. Since the electric field has both magnitude and direction, it's a vector. Like all vectors, the electric field can be represented by an arrow that has length proportional to its magnitude and that points in the correct direction. Let's take a closer look at that. Here we can see image A positive charge, has arrows pointing away from it. So that is drawing convention. This is because if we were to put a positive test charge somewhere in the vicinity of this positive charge, it will be pushed away. For image B, you can see a negative charge of equal magnitude to charge A. You'll notice that for negative charges, the field lines point inward. Again, this is because if we were to put a positive charge somewhere in the vicinity, it will be attracted towards the negative charge. For C, you can see a larger negative charge. The only thing that we can use to show that something is larger in magnitude with these arrows, because the length of the arrows do not really dictate how strong the force is how many is their closeness. So that is their areal density, or the number of lines crossing a unit area will represent the strength rather than the length of an arrow. Here's an example. Find the magnitude and direction of the total electric field due to the 2-point charges Q1 and Q2 at the origin of the coordinate system as shown. So we're going to use the equation for field, but first let's take a look at directions. Q1, how is Q1 going to affect that point at the origin? Well, Q1 is going to force it to go up. And how is Q2 going to affect the charges? Well, Q2 is going to make it go to the left. So when we're calculating the effect of Q1, we're going to call that electric field 1. We're going to put in our KQ over R squared, where K is approximately 9 times 10 to the 9 Newton meter squared per coulomb squared, times the charge of Q1, which is 5 nanocoulombs. Remember, we want to put that in SI units coulombs, so the nano is times 10 to the negative 9. And that's divided by R squared. Well, R is 2 centimeters. Again, we have to put that in SI units. So we have 2 times 10 to the negative 2 to convert it from centimeter to meter. We plug that all in the calculator and we get 1.124 times 10 to the 5 newtons per coulomb. Now for E2, to calculate E2, we're going to just look at the origin and the charge Q2. And we're using the same equation. K times Q2, which is 10 nanocoulombs, so that's 10 times 10 to the negative 9 coulombs. And the distance is 4 centimeters, so 4 times 10 to the negative 2 meters. You plug that out in the calculator, and we get electric field 2 to be 0.5619 times 10 to the 5 newtons per coulomb. To get the total, because they are vectors in the x and y direction, you have to do both directions squared, add them up together, and take the square root. Just like if we're trying to find the magnitude of a vector, we would go x squared plus y squared, all square rooted. To get the direction, it's arctan of the y force over the x force, and we get 63.4. So let's take a look at what this looks like. So here we have E1 going up, we have E2 going to the left. Again, when you're adding those two together, you have to do that the total force is the square root of E1 squared plus E2 squared, all square rooted. And then to get the direction, you do arctan of rise over run, E1 over E2. Now let's just take a look at the lines and how they're created. Here we can see Q1 and Q2, and we have a point P and another point P prime. Let's see where they get all these arrows for P prime from. We'll use point P as a reference. Now, as you can see, Q2 will cause a force to go onto P in this direction. Q1 will cause a force in this direction. So what we have is we have E1 coming from Q1, and we have E2 coming from Q2. That will give us a line tangential to the field line drawn, E. Now what they've done for you when they represent all these lines is they've calculated what direction the field will be going at every point on that line. And that's why the lines curve the way they do. So electric field from 2-point charges can be drawn by finding the total field at representative points and drawing electric field lines consistent with those points. While the electric fields from multiple charges are more complex than those of single charges, some simple features are easily noticed. For example, like and unlike charges. Since like charges repel, you'll notice there's an empty space between the two of them because of the conflicting field lines. Whereas the two charges that are unlike, I should say, they attract each other, so the field lines are pretty consistent. Two negative charges produce the fields shown in A. It is very similar to the field produced by two positive charges, except that the directions are reversed. So you know that negative field lines go towards the charge, whereas if it is positive, it'll go away from the source charge. Field is clearly weaker between the charges. The individual forces on a test charge in that region are in opposite directions. For figure B, the two opposite charges produce the field shown, which is stronger in the region between the charges. The properties of electric field lines for any charge distribution can be summarized as follows. 1. Field lines must begin on positive charges and terminate on negative charges, or at infinity, in the hypothetical case of isolated charges. The number of field lines leaving a positive charge or entering a negative charge is proportional to the magnitude of the charge. The strength of the field is proportional to the closeness of the field lines. More precisely, it is proportional to the number of lines per unit area perpendicular to the lines. The direction of the electric field is tangent to the field line at any point in space. Field lines can never cross. Let's take a look at conductors and electric fields in static equilibrium. Conductors contain free charges that move easily. When excess charge is placed on a conductor, or the conductor is put into a static electric field, charges in the conductor quickly respond to reach a steady state called electrostatic equilibrium. Free charges move within the conductor, polarizing it, until the electric field lines are perpendicular to the surface. The field lines end on excess negative charge on one section of the surface and begin again on the excess positive charge on the opposite side. No electric field exists inside the conductor. That's very important to keep note of, since free charges in the conductor would continue moving in response to any field until it was neutralized. Properties of a conductor in electrostatic equilibrium. The electric field is zero inside a conductor. Just outside a conductor, the electric field lines are perpendicular to its surface, ending or beginning on charges on the surface. Any excess charge resides entirely on the surface or surfaces of a conductor. How can a very uniform electric field be created, you might ask? Well, in order to do this, you would have to have a plate of charges opposite to each other, relatively close to each other. That way the field lines can be basically perpendicular to the plates, going out of the positive and into the negative. Consider a system of two metal plates with opposite charges on them as shown. The properties of conductors in electrostatic equilibrium indicate that the electric field between the plates will be uniform in strength and direction. Except near the edges, the excess charges distribute themselves uniformly, producing field lines that are uniformly spaced, hence uniform in strength, and perpendicular to the surface, hence uniform in direction, since the plates are flat. The edge effects are less important when the plates are extremely close together. Let's take a look at this in nature. Earth's electric field. A near uniform electric field of approximately 150 newtons per coulomb, directed downward, surrounds Earth, with the magnitude increasing slightly as we get closer to the surface. What causes the electric field? Around 100 kilometers above the surface of Earth, we have a layer of charged particles called the ionosphere. The ionosphere is responsible for a range of phenomena, including the electric field surrounding Earth. In fair weather, the ionosphere is positive and the Earth largely negative, maintaining the electric field. In the presence of storm clouds, the local electric fields can be larger and even produce lightning. At very high fields, the insulating properties of the air break down and lightning can occur. Now let's take a look at electric fields on uneven surfaces. Excess charges on a non-uniform conductor become concentrated at the sharpest points. Additionally, excess charge may move on or off the conductor at these sharpest points. The electrostatic repulsion of light charges is most effective in moving them apart on the flattest surface, and so they become least concentrated there. So here is our non-uniform conductor in a field. In figure A, the forces between identical pairs of charges at either end of the conductor are identical, but the components of the forces parallel to the surface are different. It is F parallel that moves the charges apart once they have reached the surface. In figure B, F parallel is smallest at the more pointed end. The charges are left closer together, producing the electric field shown. In part C, an uncharged conductor in an originally uniform electric field is polarized with the most concentrated charge at its most pointed end. When the charges are close to a flat surface, the charge allowing them to spread apart is greater, which is why it's more gathered at the pointed areas. Let's take a look at the Van de Graaff generator. Van de Graaff generators, or Van de Graafs, are not only spectacular devices used to demonstrate high voltage due to static electricity, they are also used for serious research. The first was built by Robert van de Graaff in 1931, based on original suggestions by Lord Kelvin, for use in nuclear physics research. Van de Graaffs utilize both smooth and pointed surfaces and conductors and insulators to generate large static charges and hence large voltages. A very large excess charge can be deposited on the sphere because it moves quickly to the outer surface. Practical limits arise because the large electric fields polarize and eventually ionize surrounding materials, creating free charges that neutralize excess charge or allow it to escape. Nevertheless, voltages of 15 million volts are well within practical limits. Here's a figure of a Van de Graaff generator. Battery A supplies excess positive charge to a pointed conductor, the points of which spray the charge onto a moving insulating belt near the bottom. The pointed conductor B on top in the large sphere picks up the charge. The included electric field at the points is so large that it removes the charge from the belt. This can be done because the charge does not remain inside of the conducting sphere, but moves to its outside surface. An ion source inside the sphere produces positive ions, which are accelerated away from the positive sphere to high velocities.